Welcome to this fourth week of the Smart Grid Technologies course. Change of speaker today and also change of TA. So I would like to introduce the two main TAs in the back. Shonak, who's also our Zoom master. This course will be recorded and posted online. And Ludovic, who will be helping with the TA, with the software assignments. So this week and the coming 2 other weeks, so during 3 weeks, we will be organized as follows. We'll teach on the regular slot today, and towards the last 30 minutes of today, you can have time to take the quiz. So the lecture is accompanied with a quiz online, and the lab, which is posted already, you can already start it. So about the quizzes, the rules are the one you know. You are expected to take the quiz with a passing grade, although the grade does not count for the final grade of the course, and you're allowed to take up 3 attempts. After the 3rd attempt, if you don't pass, you have a problem, you have a deadlock, and you have to speak to me to resolve the deadlock. And speaking to me might involve giving you an oral quiz to make sure you really master the stuff. But hopefully that happens to nobody. The quizzes are chained. You must be up to date. You must have done this week's quiz to be able to upload the lab. And next week, you will also need to be up to date with this week's quiz to do the following quiz, etc. The idea of this is to force you to do online training by small pieces rather than having to digest big things altogether, which is probably not doable. What is the objective of this part? This part is a bit atypical in a smart grid course. Smart grid is essentially an electrical engineering topic where you will speak of phasors, PMUs, signal processing, etc. We'll speak of optimal power flow in a few more weeks. But all of this is connected through a network. So we somehow have to put our things and our fingers into the communication part. And the minimum part is what we will cover in this series of lectures. So the goal is to be able to have a mental image of the main ideas that underlie TCP-IP so that you can use it well. Of course, you will not be an expert in communication systems and in TCP-IP after taking this module, but you will know already much more than most people, including most engineers, and you will be able to go on the internet if you need to know more. So what is more difficult in TCP/IP is to have the correct ideas about how the architecture is organized. This is what we will follow, we will discover today and next week. Of course, there are zillions of details that we will not follow in detail in this course. For example, if you buy a router of a specific, from ABB, for example, to interconnect your PMU devices, you will need to read the manual of how to make it work. But in order to read the manual, it will be much easier for you to read it and understand, because you will understand what are the basic things that it is speaking about. There are 2 books that I recommend. They are not necessary. You can take this course by simply having the slides. You can also look up on the internet where the Wikipedia pages on any topic are usually fairly good for the topics we cover here. And if you want to know more, there are those 2 books that are available online. This one is not officially available online, the last edition, but in practice it is. And this one is an open book, so you can really find it online here. This one is more superficial. It gives the main ideas, but some of the details are not necessarily well covered. Here it goes a bit deeper. So let's start. Let's start first with a global view, which is called the layer model, and then we will go one by one into some of the main, I will zoom on some of the main topics. You may have heard the layered model of communication systems. It's a system with some order in the layers, and the course will not necessarily follow the layers, because by experience, this is not what is the most useful way of learning things. So computer communication is about letting things communicate. I mean objects or people communicate over the network. And of course, we all know how to do it and how to use it. Uh, Essentially, it's organized in what is called client-server communication. So you have clients, which are typically small, but not always small objects or smartphones, or the PMUs, that communicates with servers that are, for example, the websites or the PDCs, when the PMUs send data to a PDC here. Why do we have this terminology, client-server? Well, this is solving a bootstrap problem of communication. If I want to speak to you, we have to agree on a place where we are together. So we somehow, through the mechanism of EPFL, agreed to be here at the same time this morning so we can speak together. If you want two machines to speak together, you have the same problem. They need somehow to be ready for speaking. You cannot simply start a device that will speak to another device. Chances are the two devices are sleeping when they're doing nothing, so the communication will not work. How do you wake up a device? Well, you need to press a button somewhere, but this device must be somehow ready to receive messages. That's what is called the function of a server. So a server is a device that is waiting for messages to arrive and to do some job, as opposed to a client that doesn't have to wait, which does it on demand. When a client has something to send, it sends it to the server, and the server is ready listening to things. So that's the definition of client and server. So that's I would say, the visible and useful part of computer communication. We have a PMU and a PDC, the PDC, phaser data concentrating unit, that has the goal of putting together all the PMU measurements and aligning them, and from that to do what is called state estimation, that you will discuss in more details in the following modules. So that's the useful part of the communication system. But for this to work, we need to interconnect all those devices, clients and servers, through an infrastructure, which is the network itself. So it has cables, Ethernet cables or USB cables for things like PMU, sometimes wireless links for things like your smartphone or your PC that's connected over Wi-Fi, base stations, and all those things are interconnected by routers and something that is a bit underground, but is needed in a smart grid context, will need to be interconnected. For example, PMUs are typically connected via Ethernet cables to Ethernet switches that are connected to routers that are connected to other devices like the PDC. What we will discuss is what is the organization of this insofar as it affects end users. End users is an engineer who's writing program from, for example, a PMU that is writing the program that has to send the data. So the way these things are organized influences the way we write such programs and we interact with the networks. That's what we will discuss today. So here is the traditional description of how the internet technology is organized. It is called layers. So we see here, for example, all the software and hardware that runs on a smartphone. It is organized in a number of layers. The number of layers is not always agreed upon to be the same, but typically most textbooks will consider there are 5 layers: application, transport, network, MAC, and physical. We will discuss each of them in as much detail as we need to be able to have a good mental model. What is the definition of a layer? Well, a layer is nothing else than the classical problem we have in any complex system, which is modularity. We need to make a system made of pieces called modules that have well-defined interfaces such that I can interact with the module by knowing only the interface. This is what we do when we interact with our PC or our smartphone. We don't need to know all the details of how the operating system works to be able to send an email, for example. But we need to know what is the concept of a file, a directory, a permission. Those are things that affect us. So we need to know something which are essentially visible at the interface. That's the first principle. That is common through all complex systems, and in particular in software systems. Here we have communicating systems. So communicating system means they have 2 types of interfaces. They have on this diagram the horizontal interface, which is when a module, for example, the application layer. The application layer is your web browser and the web server. There are 2 faces of the application layer. When a web browser speaks to a web server, it uses an interface, which is a software interface, which is defined by the HTTP protocol. The HTTP protocol, Hyper Transfer Text Protocol, is the protocol that defines the internet. So it says what is the format of the messages you send, and all the interactions. For example, when you go to a web server, you expect to send a verb called get, followed by the name of the page you want to download, and that is the interface. So by nature, because we are communicating, layers communicate with other layers that are at the same of the same nature. So an application layer entity speaks to another application layer entity. In addition, an application layer entity speaks to the transport layer, which provides a service to it. We will discuss about that in a second. The transport layer is what we do when we implement the software. So we need to send data. How do I send data in a computer? Well, I use the interface of the transport layer, which in most systems is called the sockets interface. That's the one you will exercise in the lab. And similarly, the transport layer speaks to the network layer to have the data sent, and the network layer speaks to other network layer entities. Here you see a difference is that the application and transport layer are end-to-end. We expect them to be present only in client and servers, whereas the layers below, they build really what is called the interconnection infrastructure. They are more intermediate systems. For example, if I send a piece of information from here to a remote server, I will not have a direct network layer connection or a direct physical layer connection. I will go by a number of intermediate systems that are called routers or switches. So this is what we will discover in detail. So the first thing to remember is that the names of those 4 layers, physical, MAC, network, transport application, and this organization of layers. In the rest of today and next week, we will discuss all the details, what we need to know about all of these applications. The words TCP-IP have to do with the names of the network layer. It's called IP, that's a synonym. And the transport layer has 2 modules, 2 variants, TCP and UDP. And the most spectacular one, because UDP is simplistic, is TCP. So that's the name of the protocol that is used here. I'm using the word protocol. What does a protocol mean? Well, a protocol in this context is exactly the specification of the format and of the rules at this interface between 2 layers, 2 entities that are sitting at the same layer. For example, HTTP is a protocol. It says exactly what is the format of the messages that a web client sends to a web server and what is the expected actions that result from sending such a format. What is the format of the error code, the 404 error that you receive? All of this is part of the HTTP protocol. Similarly, when a transport layer entity speaks to another transport layer entity, it uses a protocol, which is, for example, TCP. And IP is also the rules of how a router and a host speak to each other. That's called the Internet Protocol and Ethernet, etc. We'll cover all of those in detail. Quasi all networks today use this. I say quasi, that means there are some who don't. 20 years ago, there were many who did not use. For example, if you have a Macintosh, 20 years ago, a Macintosh was not using TCP/IP. It was using AppleTalk, which was not at all TCP/IP. It was doing the same thing, but differently. So it was not using, it had a transport layer, an application layer, a network layer. The network layer was using AppleTalk things, which is Macintosh type of things, much easier to use, no easy, no complicated address like we will discuss today, but it was not scalable. AppleTalk was made to connect perhaps your 20 computers at home with 10, or in an office with a few printers and a few backend servers, but it did not scale to the global internet like IP does today. So this has disappeared. And there were zillions of things like AppleTalk, DECnet, IBM, they all had their own way of things. Those things have disappeared, but in the smart grid technology, there are in corners a few of them that remain. In particular, there are sometimes protocols that don't use IP in substation automation. We will not discuss them in detail because they tend to disappear because they don't add value to doing it in TCP/IP. They are just here by the result of evolution. So the application layer is fairly easy to imagine what it's doing. That's the software that runs in your web browser and in the web server. That's the application layer. Also, PDU sends data to a PDC. That's the smart grid application layer that does it. Now, the application layer uses the transport layer. So as the first mysterious thing, what is the transport layer? Well, the transport layer is providing a programming interface to the application layer. Remember that the layering principle means that any layer, except the ones at the top, offers a service to the layer above it. So the goal is to simplify the job of the application layer. When you send packets, when you send data from one computer to another computer, you need to solve zillions of issues. Like, I mean, at the end, in order to send data, you don't send a page or an object or an image, you send bits. So how do you write the bits, in which order? All those details needs to be solved. And if you don't have a common layer to do that, everybody will solve it in their own way, and there will be chaos. So in order to avoid this chaos and also to simplify the programming job of the application layer, there is a transport layer. So the transport layer says that if I need to send data from A to B, I will, it will say exactly which software I can use and what are the usual terminology to do it. The transport layer exists in two variants. That's the beginning of the complexity: UDP and TCP. I'm sure those are words you've already heard. UDP is the simplest of all. It does nothing else than simply solve software problem of how to put the bits in which order. Is it the first bit first? So if I have a byte of 8-bit, do I write it first or last? That very simple set of things is the only thing that UDP does. Plus, UDP adds the concept of a port number. So a port number is something that allows for two machines to communicate when they have more than one job in parallel. For example, imagine a PDC. PDC is talking to a number of PMUs, so it receives data from many PMUs. And also, a PMU similarly sends data to a PDC, but a PMU may do other things. You don't expect to log into a PMU to navigate the web. It would be a very bad idea for security purposes and from performance viewpoint. But certainly there are other things you do on a PMU. Can you imagine one of them? Well, one of them that, yes, time estimation, exactly. So there's a time protocol that there is another process that probably runs over UDP to receive the time correctly. So that's an example of a maintenance job. That's something that's underground that we don't really care very much about the semantic of application, but we need it for the PMU to work. And also once in a while, and perhaps every week even, you will need to patch the software of your PMU, because the PMU will probably use cryptographic software. This cryptographic software needs to be patched because there's an arms race between the attackers and the defenders. And whenever we find a weakness in software, we fix it, and then we need to deploy the patch in the PMUs. Plus, you're working in the lab on your PMU, so chances are you always improve your signal processing software, so you want to modify it. How do you modify the software? Well, you need to transfer your software code, large number of bits, into the PMU. You don't do that over the same application as you do the normal PMU job. So there is and also perhaps you want to log into the PMU to see if everything is okay. You will do an SSH session into the PMU. So you will do a number of things in a PMU just for maintenance purposes. So there are a number of tasks, or in computer science, they're more often called processes, that work in parallel. Now, when you send a packet to a PMU, you need to say, is this a packet that the PDC is sending as an acknowledgement that the phasor measurement unit measurement has been received okay? Or is it a packet that instructs the PMU to report something like, is the PMU up and working? That's what you do when you log into the PMU to verify its status or to configure it. So that will go to different processes. So if you want to identify and each of those processes is in an application layer of its own. So in order to know to which application layer the packet will be going, or within the application layer to which sub-function it is going, we use what is called a port number. So port number is a 32-bit number that is associated with any activity that you do. So when you use the transport layer, you will do things like you say, I want to send data. I am the phasor measurement unit application. Give me a port number. we don't care which one it is here, and then send it to the port number of the PDC. I need to know the port number of the PDC. So typically, the port numbers of servers must be known in advance. That's the principle of client-server communication. Remember, the server is expected to be up and running and waiting for things to come. So the simple way to do it is also for the server to follow a well-known port number. So the PMU must be programmed with the port number of the PDC, and then the data, when they are received by the IP layer, will be forwarded to the UDP layer with the information on the port number, and the port number will be used to send the data to the correct process in the application layer. Why do I spend so much time discussing a minuscule detail of the application layer, of the transport layer, which we will rediscuss in detail a bit next week, is because for reasons that will be completely obvious next week, this is visible everywhere. So the port number will be visible even if you're not programming the application layer. It will be visible in a number of instances, as will become clear a bit later. So first take-home message here, the transport layer uses port numbers to differentiate the processes inside the machine that need this. So that's all for the global overview. Now we will dive into the network and MAC layer, which are those things here. The network and MAC layer are the interconnection network. Those are the things that allow to build a network. So first, the network layer. The network layer interconnects all systems in a given universe. So what is a universe? Well, for most of us, except perhaps in the smart grid, for most uses, it is the internet. So the internet is meant to be a globally interconnected system. So I can send a packet to a server in California or in China or anywhere, perhaps not North Korea, but most countries are part of this global universe. Sometimes we have a special universe. For example, in the smart grid network, you may want to separate your production network. So typically, industrial networks tend to be separated from the internet. So the smart grid network, you want as much as possible to separate it. So that universe, in that case, is the smart grid network. Similarly, a train management or a railway station management network, you hope it is separated from the main internet so that you can't hack it, essentially. So within these universes, the protocol, which is called IP, stands for Internet Protocol, follows a number of principles that we will discuss in detail. So the first principle, which is a design, which illustrates the main design. First, every interface has a number called IP address. So what is an interface? Well, this PC is connected over Wi-Fi now, so the Wi-Fi interface has one IP address. I could also put an Ethernet cable into the PC. That would be a second interface that would have a second IP address. So every communication interface, which are things by which you communicate, wireless adapters or cable system, has a number, like a telephone number, essentially. But it's called the IP address. Sometimes when you read blogs on the internet, people call it IP. What's your IP? It's like if I ask you, what's your telephone? It means what's your telephone number. Here it's the same. When people say IP, they mean IP address. And it must be unique in a given universe, of course. So all IP addresses in the world, in the global internet, have to be unique. Then the data received from the transport layer, remember the layering principle, the transport layer allows the programmer of the application layer to send data through an interface. Then the transport layer has blocks of data. Then these blocks of data must be broken into chunks that are called packets. So that's the main principle of the internet, this principle of packet switching, that the data, as soon as it leaves a machine, is in the form of packets, which are relatively large by the technology of 20 years ago and relatively small by today's technology. Today, the maximum size of a packet is in principle 1,500 bytes, so 12,000 bits. A byte is 8 bits. That's in principle the maximum size. I say in principle, it depends on the configuration of the systems. It's not always that number, but as a first approximation, that's that number here. So if you have to send a video file, then you will need to break it into thousands or hundreds of thousands of such packets. And each of those packets will navigate over the internet. In order to navigate, every packet contains a destination address and also the source address. The source address is used essentially at the destination to know whom to respond to. If I connect to a web server, this web server will know where to send the reply by looking at the source address that's contained in the packet. That's the principle of the postcard. So this is imitated from the postcard system of the post office. Except with a postcard, usually if we have a big message to send or a textbook to send, we don't write 20 postcards, which every postcard containing a page of the textbook, but that's how the internet works. And the systems that you expect to handle this are called routers. So you don't expect that my web client is connected to my web server. You expect that the web client is able to send a packet via Ethernet or Wi-Fi to a router that will send it to another router, etc. That will essentially send it to the destination. So we expect that there are so-called switching systems called routers that receives packets that are intermediate systems. They are not the source nor the destination. Their job is to allow the network to operate here. That was invented in 1973. So you see, that's 50 years ago. So here's an example where I'm sending a mail to someone, and you see that the mail is perhaps containing a big image that is broken into packets. So here I'm showing client and server at the periphery, and the boxes in the middle are routers. And if I'm sending a mail, I'm sending them to my mail server. The mail server will eventually send it to another mail server, who is the mail server of the destination, of the recipient. And the mail server will send it to the PC or to the smartphone of whoever is sending it. So here we see that we have 4 end systems that are involved. The web client, the mail client that sends it to the mail server that sends it to another mail server, and the mail server sends it to the mail client. That is very typical use of things. Normally in the internet, since we forward data at the IP layer, we have what is called the end-to-end principle. We want clients and servers to send the information directly from one to the other, not going via zillions of intermediate servers, for example. But here it's typically not possible because my mail software is not always up and running. My smartphone here in my pocket is sleeping. If you send me a mail now, my smartphone is not able to receive. So to solve this problem, you send your mail not directly to me, but you send it to your mail server who is expected to be always up and running 24 hours a day, every day in the year, will send it to my mail server, which probably are both the same server, which is EPFL server. And then whenever my smartphone decides that I want to get the mail, I will connect to it. So that's the typical thing. Did you observe anything special on this animation? They did not follow the same route. So that's the principle of this postcard system. If I send, every packet is a standalone entity that can follow possibly different paths on the internet. It can happen, as we will see, it's not forbidden, but it will impact performance. For example, when we send large amounts of data with TCP, as we will discuss, that impacts performance, but that is possible in the internet today. Most routers will try to avoid this, but it is possible. In particular, the idea is that this interconnection layer is largely independent of the thing here. For example, if one router goes down, so you have to imagine the internet is huge systems. There are millions of devices. So what's the probability that in a given interaction, if you're log into something and your session lasts an hour, was the probability that at least one of the devices on the path has a problem and boots, or the software is patched, or something happens that causes an interruption of service? The probability is large. So this design, has been designed to allow for this. That's why the packets here can be independent entities. If one of the routers goes down and another path is found, the packet will find its way to go to another path here. So we cannot guarantee that the path will always be the same. That's a consequence of allowing the system to reconfigure smoothly and completely independently, which is the success of the internet. That's why the internet was a success compared to other technologies, is that it has the ability to repair errors easily and reconfigure. A few words about the addresses. So I said IP addresses are like telephone numbers, but they have a very different syntax. So there are two addressing formats, IPv4 and IPv6, which we will discuss both in detail. And here, that's really something we're exposed to. So we have to understand them. So the IPv4 address is the last but one version. The current version is IPv6, but the most widespread version is still the old one. So it is 32-bit long. So every IP address is 32 bits. And it is written in what is called dotted decimal notation. Dotted decimal means that we write a block of 32 bits as 4 bytes, 4 blocks of 8 bits. And every byte is written by using its decimal representation. So if, for example, if I have this sequence of 8 bits, which is here, 10110010, we interpret this as the expansion in base 2 of a number. So this is 0 plus 1 times 2 plus 0 times 2 to the power 2 plus 0 times 2 to the power 3, etc. It's a bit painful, but that's... So it's, we interpret that as a number, and if we expand it, 2 plus 16, which is here, 1 times 2 to the power 4, plus 1 times 2 to the power 5, plus 1 times 2 to the power 7, that gives 178. So instead of writing this list of 8 bits, we write 178, which is, for example, this block here. IP addresses at EPFL, most of them start with 128, a few of them with 129, but 128, 178, 151.1, that means this is this sequence of bits here. This is totally obsolete. This is because it was done in the 70s. Today, we would use hexadecimal digits. An hexadecimal digit is based on the observation that if we use, well, the observation first is we don't want to use base 2, which is a natural thing that computers use. But we don't want to use it because it's very long, and sequences of zeros and ones are quasi impossible to read and write, right? If you say, that's my IP address, chances are you will not be happy writing this down, and would be a lot of errors. So base 16, hexadecimal digit, is based on the observation that if we take as base not 10, like we do because we have 10 fingers, but 16 because that's close to 10 and is a power of 2, that means that a block of 4 bits here is represented by 1 hexadecimal digit. So, for example, so hexadecimal digits means we count from 0 to 10 by using the 9 digit, from 0 to 15, sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 10 is letter A, 11 is letter B, etc., until F, which is 15. So we use 16 symbols. If we had 16 fingers instead of 10, this is how we would count. But nature has given us 10 fingers, so it's inconsistent with binary computers here. But all computer science uses always hexadecimal digits to write bits. Because, for example, if I have 8 bits to write, that corresponds to 2 hexadecimal digits. So if IPv4 were invented today, we would not use this notation for the address, 128.178.151.1. We would use this one, 80B29701, which is equally ugly, but is much shorter. And we don't need the dot, because the dots are needed here, because if I don't have the dot, what would happen? Well, I would not know, for example, if I have 151.1, I would not know whether it's 15.11 or 151.1. So I need the dots to be able to eliminate the leading zeros. If I have the discipline to always put 001 instead of 151, then that would not be needed. Also, as you can see, it is less compressed. I need 3 digits whereas with hexadecimal, I need only 2 characters here. So this is I would say, the state of the art here. This is how IPv4 does it for us, and we'll have to live with both. So an IP address is something like this. There are special IP addresses that we must know. The special IP addresses are, in particular, the so-called private addresses. Private addresses those ones are called public addresses. So a public address is like a telephone number. I mean, you don't choose your telephone number. It's given to you by your operator. So the same for IP addresses. Your IP address, you don't choose it. It's given by your operator, which is today the same as a telephone operator. So if at home you are a customer of Swisscom for your ADSL access, Swisscom gives you an IP address. You don't choose it. Perhaps if you pay a lot, you can ask Swisscom to give you a specific address that ends with your birthday or something like this. But still, it will be within the block and the prefix that Swisscom is allowed to use. All EPFL address starts with 128.178 or 128.179 here. So the only thing you can negotiate with EPFL would be the leading terms here. So an EPFL, an IP address is allocated at the top by an entity called ICANN that gives blocks of address to the different parts of the world. And then in Europe, for example, there is an entity called RIPE that allocates to different operators that run in countries a block of addresses. So Swisscom has received a block of addresses and allocates to you one of these addresses. EPFL also has received a block of addresses, which is this one. Private addresses, in contrast, belong to nobody. Everybody is allowed to use them. But the meaning is you use them in your private network. For example, if you build a smart grid that has 2,000 PMUs and 20 PDCs, you can give them private addresses as long as it's your private universe. It's not connected to the rest of the world. That's very convenient for debugging for a number of reasons, and also to make private networks that are truly not connected to the global internet here. There are 3 blocks of addresses, 10 dot something, 192.168, and 172.16 to .31. So anything that's in these blocks, and you can use any of those 3 blocks freely as you want. Typically, if you look at your IP address when you're at home, you will probably have an address of this type. This is for fairly small network, and that's the software that Swisscom has probably pre-programmed into your ADSL router. And at EPFL, in a smart grid, for example, we will use those addresses typically. There's also a special address, which is this one, 127.00.1, which is called localhost. It means this machine. So if a process A sends a packet to a process B to this address, that means A and B are on the same machine. You can say, well, what's the point? The point of communicating is when you're not on the same machine. Well, first, not always. You can have what is called inter-process communication. You can have 2 applications that communicate with each other. Whether they are on the same machine or not, they may want to use the same software. For example, you can have a web client that is sitting on the same machine as your web server that you will do, for example, when you are in the debugging phase. When you're debugging your system, you may want to put both on the same machine and try it by giving IP address, and you will be able to use this IP address. So those are addresses we will very often use. So that was for, yes, question. How do you, the best is to have a calculator. So all calculators do that today. So anything called a scientific calculator will have a mode called decimal, binary, hexadecimal. If you type a number and you hit hexadecimal, and if the mode was decimal, you type it as decimal. If you type hexadecimal, it will convert it to you. Now, if you're interested in how do we convert, well, here is the rule. The rule is that you expand that according to the powers of 2. And base hexadecimal is according to the power of 16. So B2 means 2 plus B times 16. Just like 151 means 1 plus 5 times 10 plus 1 times 10 to the power 2. That's what base 10 means. Base 16 means the same. This is 2 plus b. b means 11. So that's 2 plus 11 times 16. That should give exactly 178 in decimal notation. It's painful. In principle, you use a calculator for that. But there are some special things we might want to know. For example, all ones everywhere. If you add 1 to this, that gives, it's like 999999 in decimal. If you add 1 to 99, you obtain 100. So that's the last number before the one that would be 1, followed by 80. So that's 256. That's 2 to the power 8 minus 1. So that's 255. In hexadecimal, a block, now the mapping hexadecimal to binary is easier in the sense that you do it by entire blocks of 4 bits. A block of 4 bits correspond to exactly 1 hexadecimal digit, which is not true for binary. Binary, it's where the digits start is completely unrelated to the separation. And 11111 is the number F. It's 15. It's the largest hexadecimal single digit number. So FF is the same as all bits equal to 1 and is the same as 255. That's something we need to remember because we will see it in the configuration of machines, for example. That was the first principle of IP. So the first principle was we use packet switching. Every packet has a source and destination address, and the addresses are 32-bit long systems with IPv4 at least. Second principle is called longest prefix match, and that's really what made the internet scalable. Longest prefix match means that every system, in particular every router, has a table and to know what to do with packets. So remember, the principle is when a computer sends a packet to another computer, like here, for example, it doesn't send it directly over a long cable, but it sends it to a router that sends it to another router, etc. So the routers, the intermediate systems, have what is called a routing table. It turns out that the hosts, the client and servers, also have a routing table. One of the principles of IP is that, like in Unix in general, that you don't really make a difference between end system and intermediate system unless there's a strong need for making that difference. So hosts and routers have a routing table. Let's zoom on the routing table of this box here. This box is a router that is sitting at the interface of EPFL, that's the EPFL network, and the switch network. Switch is like Swisscom. It's an operator that is a special one that's funded by the Swiss government primarily to interconnect research institutions and universities and schools. So this router called ED0-SWY, so which means épine dorsale 0, backbone 0, and switch. So that's the reflection that it's just sitting in front of the switch network and in front of the backbone of EPFL. If we look at its routing table, here I'm giving a simplified view of it. It contains 3 lines. So a routing table contains columns, which correspond to fields. There may be many details that we won't discuss here, but the main details are the destination, the next hop, and the interface. So there are, in fact, 3 columns here. They are put together here. What does it mean? It means for every packet where the destination address corresponds to this, here is what to do with the packet. And what to do with the packet means 2 things. Where to send it, so there's an interface number. Here, to make the story simpler, I put south, but in computers, they are not called south. They are called with names such as E0 or ETH1 or UN1. So they have letters that correspond to ETH0, stand for Ethernet 0. That's the name of the physical interface here. So here it means any packet that has an IP destination address that matches this string here should go to the south interface. South interface is here, and should be going to whom? To this IP address. This IP address is this one here. So it means if this guy has a packet with a destination address that matches this, it should send it over the south interface, and it should send it to the router that has this IP address. Here, we don't know whether it's the router or the final destination, but it just says to the system that has this IP address. Now, a few words about this, the destination. The destination is not one IP address, but is a prefix. Prefix means it's not the full address, but it's anything that starts with the first 24 bits of this address. So the /24 means consider only the first 24 bits of this. Here, this is a string of 3 dotted decimal integers. The dotted decimal integer represents 8 bits. So that's a string of exactly 24 bits. So we could say the /24 is useless because that's exactly 24. But because of the hexadecimal, the dotted decimal notation, if you want to express only the first 25 bits, for example, you will not be able to write a number of decimal digits that corresponds to exactly 25 bits. So we put the /24 to be explicit here. Here there are 2 other entries, 128, 178/16, and another entry which is 0/0. So an IP address or an IP prefix 0 means invalid. So it's not a valid address. The IP address 0 is not a valid address. But the /0 means it's empty. So that means that's the empty prefix. Because we use prefix matching, also called longest prefix match. So what does it mean? Well, it means, assume here, COMSYS sends a packet to lemma, LRC MAC4. So it will send an IP packet to this address, 128.178.129.64. It will create an IP packet. The IP destination address will be this one. When this packet reaches this router will go to the table here and will try to match all those lines here. The first one, does it match? The answer is yes. Does it match? It means whether the 24 bits of this prefix here are found exactly as the first 24 bits of this address. The answer is yes. So it matches this here. Does it match this one? Are the first 16 bits of the address equal to 128.178? The answer is also yes. It also matches the second line. Does it match the third line? Well, also yes, because the third line is empty. So anything matches this one. You always match because you have nothing to check. So it matches the 3 lines. And the IP principle number 2 says if you have multiple matches, you take the more specific one, the longest. Which means this packet will follow the rules dictated by the first line, which means it will go to this router via the south interface. So it will be sent here. It will go here, which is the correct thing to do. Now assume COMSYS sends a packet to DISUN3. The address is 128.178.79.9. Well, the difference is that the first line does not match. The lines 2 and 3 do match. So we will send it to the longest of the matching lines, which is the second one, which means it will go to 100.3, also via the south interface. So it will be sent over the south interface, but to this router here, which will be going there. Now assume LRC MAC4 replies to COMSYS and sends a packet to this address, 129.132.66.46. That's an address at ETHZ in Surrey. And when the packet reaches the box here, what does this router do? Well, it looks at all the matches. We see this does not match, this does not match. So the only thing that matches is this one. So it will send it to the north to this interface here. So this is what this table encapsulates. What is it really doing? What is the semantic of doing this? Well, this table means that by default, send everything to the north to switch. Then second default, anything that starts with 128.178, which in practice means the wired network of EPFL. So it means if it's EPFL, send it by default to this here, which is the backbone of EPFL. With one exception, for some reason, there is one part of the EPFL network that's not on the general backbone, but is directly connected here. So that's an exception here. So this is what longest prefix match allows you to do. It allows to have default rules, and then to supersede the default by more specific things that can be nested. And that's the key to make the internet scalable. In the internet, there's 1 million different IPv4 prefixes. When we take the sum of all the prefixes that are possible somewhere, networks in California, in India, everywhere in the world, the sum of all those possible prefixes is 1 million. But we see with just 3 lines, this router is able to reach the entire internet. That is what makes IP work well and work the way it is. And that's why we have this rule here. Of course, this is only when an IP packet is received by a machine, and this machine knows it has to forward it beyond itself. If I send a packet to the address 128.178.100.12, that means to the router itself, then the router will pass it to the transport layer, will not look at the routing table because it's one IP address of itself, which is a very rare case, but is what the network managers of EPFL do. Once in a while, they might go into this router to look at statistics or to change its configuration, for example. The consequence of this is that the IP addresses must be structured. If I am at EPFL with my smartphone, I come in the morning at home, then I move to EPFL, my IP address must change. My IP address when I am at home is not an EPFL address. I'm a customer of Sunrise, so I have a Sunrise address at home. At EPFL, I have an EPFL address. So that's a corollary that the IP addresses reflects the network in which you are, which roughly speaking reflects the geography. This is why if you go to French TV and try to stream some program, they will refuse because they recognize your IP address is in Switzerland. It's a block that has been allocated to Switzerland, so they know where you are by looking at the IP address. Not exactly. I mean, I can have an EPFL address. EPFL has multiple sites in Vallis, in Fribourg, in Geneva, in Écublens. You don't know which of the sites you're in if you don't know exactly the numbering plan of EPFL, which a priori is not something public. So you just know it's EPFL, but you know it's not in France. You don't know exactly where it is, but coarsely you do. So the IP address must be depending on when you are, and that means it must be configured. When I come in the morning here, my smartphone needs to acquire an IP address of EPFL. Question? We'll talk about it next week. That's a very good question. I could well be at home and using the VPN have an EPFL address. But let's postpone this question to next week. Before connecting to the VPN, I must first have a valid IP address, which will be the IP address given to me by Swisscom, Sunrise, or whoever my operator is. So it means my address must be configured. We can do it manually. You will see in the lab some IF config or things like this that allow you to give an IP address to an interface. You can do it manually very easily. Also, and if you try to fiddle with the configuration of your smartphone, you will find a way when you go in the settings of your smartphone, you can give an IP address that you want. But of course, this is not usually very useful because you should know exactly why you do this. And this is typically done automatically by a protocol called DHCP, Dynamic Host Configuration Protocol, which is started when you join, typically when you join a Wi-Fi network somewhere, the first thing that you will do is the first thing that your software will do when it detects that there's a new interface or a new Wi-Fi network that is becoming valid, it will try to get automatically this address. And if it does, it will get, for example, an address of 128.178 when it's at EPFL. At EPFL, if you connect via Ethernet, you have to do it manually. If you connect to Ethernet, you have to ask your system manager which IP address is allocated to you personally, to your machine, and you have to type in the configuration, your addresses. So for hosts, that's either simply done automatically when you connect to a network, or manually. That's fairly simple. In routers, you need to configure not just the address of the router, but also the entire routing table. And this is done typically by things called BGP or OSPF. which we will not discuss in detail, but those are the protocols that run between all the routers of EPFL. So the EPFL system managers will not log into this router and type in the 3 entries that I gave. Those will be discovered automatically by having the routers speak to each other and discover what are the available things and how to write a routing table that reflects that. Here are a few commands that you can use in your own machine to look at that, and we'll do that in Lab 1. You will that's the kind of things you will be able to do in Lab 1. So if we conclude this first hour and plus 10, or we could build a network by connecting all systems to routers, then connecting the routers to routers. But this is not the way it's usually done. So perhaps in 20 years, that's the way it will be done. And then this course with the first hour would stop here. But today, that's not the way it's done. If you connect systems together, you connect them either to a Wi-Fi station or to an Ethernet switch. And why do we have these? And how does it combine with the rest? In particular, if I connect to an Ethernet switch, I don't need IP addresses. So those are systems that I don't need IP addresses. So I've just explained that the IP addresses are the mechanism by which we can build an entire network, but there is something else below it. Why and how does it work? Well, that's a bit of a mystery, but we will do a break now. And after the break, we will discuss the solution to this mystery. So let's dive now into the mysteries of the MAC layer. The MAC layer was created at about the same time as the IP layer, but with very different requirements. The goal is to interconnect a small number of systems. There is no need for a large number of systems. And second, it should be completely plug and play, no configuration, zero configuration. This differs from the IP layer. In the IP layer, there's a large number of configurations we need to do. We need to have a numbering plan in particular. Other than that, the principle is very similar. Every communication interface has a MAC address. A MAC address is 48 bits, is written in hexadecimal digits, because at this time the MAC was meant to be visible only by engineers, unlike the IP address, which is visible by anybody who uses the system. So we used hexadecimal numbers. The MAC address is also called a physical address because it's really the number that's engraved in the hardware. When you buy a PC that has an Ethernet interface, the Ethernet interface comes with a number put by the manufacturer at time when this was built. So we have every system has an address, which in principle should be unique worldwide. Second, MAC layer forwards packets that come from the IP layer. They are called frames at the MAC layer. And the packets, very much like the IP layer, contain a source MAC address and a destination MAC address. The source MAC address is put by the adapter at the source, and the destination address, like in IP, identifies whom the packet should be sent to. An Ethernet switch has a MAC forwarding table, very similar to the IP routing table of a router, but there is a big difference. The big difference is that that's an exhaustive list of all the MAC addresses of all the systems that are reachable in this environment by this MAC layer system. Here I'm showing a small network with an Ethernet switch with 3 systems, A, B, C, and each of the 3 addresses are written in the table here. So when A sends a packet to C, the Ethernet switch looks up the table, looks at all the entries until it finds an exact match. Hopefully the match is present. Now you could ask me, how can that be plug and play if I buy an Ethernet switch? By the way, an Ethernet switch is often called simply a multi-port, an Ethernet multi-port extender. You can buy for 30 francs at Migros. There's no way you can go into it. You cannot configure it. You cannot log into such a system. So how is this table written if we cannot configure it? Well, the answer is the switch learns it by observing the traffic. When A sends a packet to C, the packet contains a source MAC address
which is the address of A, 08, etc. When the Ethernet switch sees such a packet on interface number 1, it concludes that the system that is sitting on interface number 1 has this MAC address. So it writes in its table this address. Now, of course, when A sends a packet to B for the first time, there is nothing in the table that says where B is. In such a case, the Ethernet switch simply broadcasts the packet to all interfaces. It will simply send it to all interfaces except A, so to B and C. C will receive the packet, B will receive the packet. The hardware will analyze the destination address. The Ethernet hardware at B will see that's for me. The hardware at C will say it's not for me. And if C is not spying, is not trying to hack the network, then the hardware at C will simply discard the packet. By doing that, B will receive the packet. And in most cases, if A sends a packet to B, sooner or later, B will also send a packet, probably to A, perhaps to some other device. So as soon as B sends a packet to A, perhaps by sending an acknowledgement to the data received from A, the switch will learn the MAC address of B and will put it in this table. The next time that A sends a packet to B, it will not be broadcasted. It will be going directly via the switch to B, because now B has an entry in its table and it says it's on interface number 2 on port 2. This table is learned and it is put in what is called a cache. So this forwarding table is a cache. A cache means that if it means this is data that we have learned on the fly and we associate a timer with it. If after some time, which is a few minutes, for example, there is no traffic from A, then the forwarding table will flush the entry A and will need to, if B after that flushing sends a packet to A, then a broadcast will happen again. Why do we do this? Well, it could be, for example, that you change your mind, you disconnect A that was connected on interface 1 and you connect another system. So that will allow the Ethernet switch to learn this new address after a few minutes of time needed for the cache entry to be flushed. So altogether, this means that the switch is completely plug and play, but there's a price to pay for this, is that it does not scale. We can do this with a switch that has a few hundreds, perhaps a few thousands of ports, but certainly not millions or hundreds of millions of ports, because the tables would be huge, and the time it takes to do an exact match in a huge table would also be prohibitive. So there is no scalability. Also, with longest prefix match, we could have a network structure that would allow to aggregate by default routes, for example. Here, this is impossible. The MAC addresses have no structure. They, in fact, reflect only who manufactured the interface, but not where your system is. If I move from EPFL to home, I keep the same MAC address, and this is no problem for the switch I have at home and for the switch at EPFL that's carrying my traffic. Wi-Fi is very similar, with one additional thing. Wi-Fi has, in addition, to handle collisions. This is similar to other MAC layers, such as power line communication, that's very much used in electrical systems. Bluetooth is also very similar. Like Ethernet, they all use MAC addresses only to decide where to send a packet. But in addition, they need to handle collisions. What is a collision? Where if I'm on a wireless system where A sends a packet to B, if at the same time C sends a packet to B also, to the base station, then there will be an interference. If you're lucky, if the power received from C is much smaller than the power received from A, then the interference can be treated as noise and the signal sent from A can be decoded. But if you're unlucky, if the power of C is about the same as the power from A, or even worse, much larger, then the interference will make it impossible for B to decode the signal received from A. So there will be a collision, and in worst case, it can be that A and C are both sending to B, and none of those packets are received by the base stations, which means we have total loss of packets here. So the MAC layer in such settings has to handle also collisions. This is why it is called MAC, Medium Access Control. It has to do with serializing the access to prevent collisions as much as possible and to handle collisions that cannot be avoided. There are many ways this can be done. In Wi-Fi, this can be done using one mechanism called RTS-CTS, where when a system such as A wants to send data to the base station, to B, it will first send a very short message called the RTS, the ready to send. This very short message is sent in a way such that it is possible to decode it even if there are collisions, or at least it's easier to decode it even if there are collisions. Why is that possible? Well, imagine that you have to send a single bit, which is a 0 or a 1, and there's a lot of noise or interference around. Well, one way to send it is, for example, to send a continuous signal that is coded on one frequency, if it's 1, and on another frequency, if it is 0. And you send it for 1 million bits repeated equal to 1. If B receives such a signal, by analyzing the energy that's present in the two frequency bands, it can conclude if there's more energy in the 1 band than in the 0 band, that a 1 was sent. That's an example of how we can still decode and receive a signal, a bit of information, even if there is a large noise or interference. So using similar systems, the RTS is sent in a way that is very immune to collisions. And the RTS is saying, I would like to send a frame of a given duration, and if the RTS is properly received, it is acknowledged by B, who sends a clear to send. And this clear to send, it will be received by practically all systems. It will be received by A, who is the intended recipient, but also by C. This clear to send contains the destination MAC address of A, so when A sees it and decodes it, it sees, oh, that's for me. And now A knows it has the token, it has the right to transmit, so it will transmit the data. And when C receives this clear to send, it says it's not for me. The clear to send will contain an indication of how much time the transmission is expected to last, which depends on the bit rate that's available between A and B. And C will defer for a time that is at least as large as this time here. So that means that if this RTS-CTS handshake works, A is guaranteed to have the channel for the duration of time that is necessary for sending the packet. The packet is shown in pink. It consists of one or several blocks of data that consist of one single MAC frame, and it is also completed by an acknowledgement sent from B to A that serves to confirm that everything was okay, in particular that there was no other collisions during this time, so everything worked as intended, and this is what is used to guarantee somehow that the collision will be avoided. Of course, when B has received a packet from A, presumably the packet is not for B, but is perhaps for another system such as C, so a similar system will occur between B and C. There will be also be a clear to send, ready to send, clear to send, and that will guarantee that collisions can be avoided. Now we've seen MAC layer on the left for Wi-Fi, we've seen MAC layer on the right for Ethernet. We can build small networks, a yellow and a red one. In order to interconnect them, we can typically use an IP router. In fact, this is the classical use of IP routers, and this is how IP has emerged and became successful as a solution for interconnecting local area networks. How does it work? Well, first we put a router that has both a Wi-Fi interface and an Ethernet interface, and we give it an IP address for each of these interfaces, a different IP address for each of these interfaces. And we must inform all the machines, all the IP machines that are in the yellow or in the red subnetwork, we must inform them of this IP and MAC address of this default router. In fact, as we see, we inform them at the IP layer with the IP address, and they will discover the MAC addresses automatically. So when A has a packet to send to P, A is on Wi-Fi, P is on Ethernet, it will create an IP packet with destination address, the IP address of the printer, and you will send it to the router. Sending it to the router means it will create a MAC packet, a MAC layer frame, that will have as MAC destination address the MAC address of the router. So the packet will be received by the router. The router will look at the IP destination address and will send it over Ethernet to the Ethernet MAC address of P by using its Ethernet interface. For this, of course, we need that A knows the IP address, knows the presence of the router, which is a configuration that's needed. Now assume B has a packet to send to P, then the communication will be done by sending the packet directly to P to the IP address of P. So communication with TCP-IP always uses IP addresses, even if it's inside a local area network. Even if B sends to P, they're both on Ethernet. You could send a packet from B to P without using IP addresses, but with TCP-IP, we mandate that we always use IP addresses.
Via Wi-Fi, A needs to send the packets so that it reaches the router. Now, what is the principle of the MAC layer? It's the same as IP. To reach at the MAC layer destination, you create a packet with MAC destination address, the system. Here, what is the system? It's the router, because from the local area network viewpoint, the packet is going towards the router. So it will create a packet with MAC destination address, this address here, which is the MAC address of the Wi-Fi interface of the router. Now, because it is sent via Wi-Fi to this MAC address, the Wi-Fi protocol that we've seen before will let A send to the base station. The base station will send to the router. The router receives the packet. The packet has IP destination address this. The router goes to its IP routing table, and it sees that it has to send it to this machine here. So the router will forward the IP packet on its Ethernet interface, which is given here, and will put MAC destination address, the MAC destination address of B. So this, we'll see that the MAC addresses have changed from here to here, from yellow to red. It's a different MAC destination address, but the IP destination address is always the same. If you use TCP-IP software, communication always use IP, even inside the local area network. For example, if B sends to the printer, it will do the same thing. B will send a packet to the IP address of the printer. It will not send to the MAC address. It will send to the IP address of the printer. Now, how do the two interwork exactly together? That's what is solved by what is called IP's design principle number 3, which says that communication between hosts are machines that are not routers or switches, in the same subnet should not go via a router, and between subnets uses a router. And what IP calls a subnet is, by definition, a local area network is the same, it's exactly synonym, or it means also a collection of systems that can communicate with each other, that are able to send packets to each other using only MAC addresses. That's what we call a subnet, or that's what we call a local area network. So here there are two subnets, the Wi-Fi subnet and the Ethernet subnet here. There are two subnets, and the IP principle number 3 says that if A sends a packet to S, it should not go via the router, which could be a possibility. If I send a packet to somebody who lives in the same street as me, a postcard, I have two ways. I can walk to the house of whom I want to send it to and put the postcard into the mailbox, or I can send it to the post office who will send it to a few houses away. Two options exist. You do what you want. You don't need to put a stamp if you use the first option. That's the main difference. IP says always use the first option. If you send a packet to the printer from B, you should not send it to the MAC address of the router, because if you do that, the router would send it back to P, but you should not do it. B should not do it, which makes sense, which makes sense if we have Ethernet switches, which we have. So if B is able to send directly to P, there's no reason to send it here and back. You use more of the resources and you use more delay, so there's no reason to do it. In fact, it makes sense because IP was really designed as a method for interconnecting local area networks. This is why it's called internet and not net. It's not NP, it's IP. We use it today as a networking protocol, but it was designed as an inter-networking protocol, where 50 years ago, the networks were small. They existed only in research labs and universities, and there were things like this here. And computers were not PCs, right? I had a computer, but not on my office. I had a terminal to which I could connect to a computer that was in a special computer room. So a university had perhaps 10 computers, not 10,000. So the networks were local area networks. And the problem was, for example, how do I interconnect the DECnet local area network on which I was doing scientific computation? How do I interconnect it to the IBM network on which I was doing email? How do I send the result of a file that I have copied from the thing here? Well, I could copy it on a disk and copy from one to the other, or I put a router that uses IP. So that was really the inter-networking protocol, and hence the names come from. And we see it continues to be visible because today we connect always via Wi-Fi or Ethernet. We don't connect directly to a router, which we could do. We could have a cable between my computer and the router, or I could have a Wi-Fi base station that is always a router instead and uses IP addresses instead of MAC. That's theoretically possible, but practically it does not exist today. Perhaps it will exist in 20, 50 years. We will see. We'll probably not see it, but you can send me a message to heaven when that happens. A consequence of this is that a host must know on which network it is in order to apply this principle. If I send to the printer, I need to know, do I send to my default gateway or do I send directly to the printer? How do I know in which case I am? I need to know on which subnet I am. This is why we need what is called a configuration in every host, which is the subnet configuration, which is typically given by the subnet prefix. The subnet prefix, for example, is very simple at EPFL. For example, an EPFL address is, at least on the wired network, is 4 blocks of 8 bits. And the subnet prefix is always the first 24 bits. So 128, 178, 156, 128, 178, 80. In fact, the subnet ID is this, 156 or 80. All those hosts on the red subnet have 80 as the third byte. All those hosts on the yellow subnet as 156 as the third byte. So this is how we identify. And the EPFL system managers, they need to do the design here. They need to decide this part of the network, I will give 156 to it. That part, I will give 80. They need to do it. They need to count how many hosts maximum are possible. Of course, if you give a prefix, if you do this, that means the subnet ID is this. That means there's only 1 byte left to identify the system. So there are at most 256 devices on one subnet, not more. If there is more, this numbering plan doesn't work. So you need to do a numbering plan, and every host must know what is its subnet. In order to do that, we could do like we did in the table, the routing table. We could give a number saying 24 is the first 24 bits here. This is what we do at EPFL. But for some reasons that are historical, we don't say 24. Instead, we say 255, 255, 255.0. That means exactly the prefix, the subnet prefix is made of 24 bits because it's a mask. If you take a sequence of bits, all equal to 1 in the position that identify the subnet prefix and equal to 0 in the rest, you translate that into dotted decimal, you obtain what is called the subnet mask. It's very contorted. It was done 50 years ago. Now today we would say /24, but that's how it's done. And one lesson we learn in networking, when you do something once, the first time you do something, be very careful how you do it, because chances are it will stay forever. So chances are you do something quick and dirty, and then it's quick, certainly, but if it's dirty, it will remain dirty forever. So changing things are very expensive, and after years, people say, oh yeah, why would I change this? Also, most people, what happens is most people did not take this course, so they have no clue of those things. They just know there is 255, 255, 255, don't know what it means and where it comes from. So at EPFL, that's the configuration we typically have. At ETH, the subnet prefix is 26 bits, which is considerably ugly or smart, depending on ugly from the viewpoint of somebody who doesn't care about computer networking and bits and bytes, and smart for somebody who loves those complexities. So, which means this is the prefix, because 192 is the binary, the decimal representation of this number, 128 plus 64, that gives 192 here. So this is what you see in your configuration here. A practical consequence is that I mentioned the fact that routing tables exist in hosts also. A host will derive its routing table automatically from its subnet mask and its IP address. For example, if I am a host here, 128.178.156.23, I must configure that my subnet mask is 24-bit long. And as a consequence of this, my operating system will automatically add into my routing table one line that says that anything that starts with 128.178.156/24 is what is called on-link, which is yet another synonym for in the same local area network or in the same subnet. So the most difficulty is the terminology here. So on-link means everything that has this IP address is on-link with me, means it's in the same subnet as me. Which implicitly means if I need to send a packet there by IP principle number 3, I should send it directly. And sending directly, it means sending to the MAC address of this destination that I have. Otherwise, by default, I send to my default router here. So when A has a packet to send to P, to the printer, it receives from the transport layer who had received it from the application layer of the destination address. And then I look at the routing table here. Longest prefix match sends there's only the default route. Therefore, I use the default route. I have to send it to this address, which is the IP address, Wi-Fi IP address of the route. Sending to this does not mean that I put IP destination address equal to this. Remember the postcard principle. When you send a postcard to the post office, you don't put as destination address the address of the post office. You put as destination address the final destination address. But you must find a way to go to the post office. So you configure your GPS on your bicycle to go to the next mailbox or the next post office. This is what you do here. You put as destination MAC address the MAC address of the router's Wi-Fi interface here. Similarly, if B has a packet to send to the printer, it goes into its routing table that has been configured from its network mask and its IP address. And now there is a match with this. that says it's on link. So when B has this packet to send, it needs to find the MAC address of the printer and send it directly to the printer here. How do I know the MAC address of the printer? Well, the MAC addresses, by principle of the MAC layer, everything should be plug and play. We should never have to configure a MAC address. We may want to if we're a hacker, we're trying to hack the system somehow. We want to break or do special things. But as a normal user, we should never see MAC addresses here. So there must be an automatic way. This automatic way is called the address resolution protocol. When B has to send a packet to P, or A also has to send a packet to P, then A has to know what is the MAC address of the router, and B has to know what is the MAC address of the printer. Well, how does it do? Well, simply by sending a broadcast. The first time B has to send a packet to P, it doesn't know the MAC address. It knows the IP address, that's done in the configuration of the printer, but the MAC address is not done there. So instead, B will send a packet that is broadcast to the entire subnetwork. There's one special MAC address with all bits equal to 1. In hexadecimal is FF everywhere. If you send a packet to this MAC address, it is sent to all machines into the system here. We see that Ethernet switches do that a lot. They do that, not a lot, but they use that to solve a number of configuration problems. At the beginning of their learning phase, when they have not yet learned all MAC addresses, they broadcast. Here it's similar. We don't know whom to send this to, so B will send a broadcast packet that will be received by the printer, by also the other computer, by this device here, and also by the router. If nobody is hacking the system, only this broadcast will be received by all systems, but the operating system will see this is an ARP packet asking what is the IP address here. If nobody's hacking your system, there is only P that has this IP address. If nobody's hacking it, and if you did no configuration mistake, because IP addresses are configured, it's possible that two machines have the same IP address, in which case you will have big problems in your network. Probably it will not work most of the time. So normally only P has this IP address. It will receive the ARP packet, the operating system, or very often this is already offloaded in the Ethernet communication adapter, will see that this is an ARP packet and will reply by sending an ARP reply that is sent to the MAC address of B. How do I know whom to send it? Well, in the MAC packet, there is a MAC source address. So it's sent to the MAC address of B with the reply, that's me, I have this MAC address. So now B knows what is the MAC address of P. It will keep this in what is called an ARP table or ARP cache. It's called a cache because it means we keep a cache is whatever we learn on the fly, and we keep it for some time. So as long as B and P communicate, for example, if B continues to use the printer will send acknowledgements that the packets have been well received. So as long as B obtains evidence that the MAC address of P is this one, the cache is renewed. And if that happens frequently often, then the ARP will never be used again. We will use only once at the beginning. If for some reason B and P remain silent for a long period of time, the cache will be flushed. The entry will be considered to be too old, and B will need to do an ARP again. Or if you change your printer is dead, you buy a new one, but you give the same IP address to the new printer, then at the beginning it will not work. Well, B will try to send a packet, it will not work. So perhaps during 20 minutes, you are unable to use your printer. But after some time, the cache at B will decide that there was no confirmation of the MAC address of P. The cache at B will be, this entry will be deleted, and it will work again. This is why, because of things like this, sometimes we need to wait a bit until it works, after resetting things, until it works again.
Or you like already system like
No, it's part of the configuration of the system. Whether you can change it or not is not so obvious. I guess on an iPhone, Apple iPhone, probably it's hard to change. On the Linux PC, yes, you can change it as you want. Yes?
Make addresses
claim that my IP address is 128.178.80.49. Will the system be stopped by the admin?
The question is, what happens if I have another machine than P? For instance, this one says I have the same IP address. Then it will break. It will break. So it's non-deterministic what happened, depending on which ARP reply is received first. You might send the device things here. So that's a known method of attacking a system. You insert yourself into a Wi-Fi network with a very fast and very good, you insert yourself very close to the Wi-Fi station to be sure you're more likely to receive the ARP broadcast before other things, and you reply before, and then you receive all the data.
What if others respond in a very few seconds later and the system be locked or?
No, B will, depending on this, but I guess industrial grade systems will simply declare that this doesn't work. If you receive two ARP replies with different addresses from the same thing within a very short time, probably, I'm not sure, I have not tested that, but probably you should declare this is suspicious and stop communication. If we put all of this together, we see that IP has some configuration. An IP host must be configured with its address. That's what we've seen at the beginning. Also with its subnet mask for every interface. With its IP address of the default router. And also, as we will discuss in a few more minutes, with the IP address of several DNS servers. And in all cases, if you are in charge of designing your IP network for your smart grid, for example, you have to decide what are the subnet masks, what are the lengths, what you need, and what are the prefixes allocated to each subnet. You need to do what is called a numbering plan. It's not, nobody will do it for you. What will be done for you is automatic configuration of all the hosts. You need to have a DHCP server for that, in which you put your numbering plan. You will write the configuration file of a DHCP server and say, for example, all the yellow systems, the ones that are on Wi-Fi, they should receive this prefix. All the red things, the ones that are on Ethernet, they should receive that one. But that's your job of doing that in your DHCP server here. So much for me speaking. Let's try a few online quizzes in class. I'm using SpeakUp. So if you don't have it yet, you can either, if you have the SpeakUp app, that should work perfectly. Otherwise, you should go to, in a web browser, to this address, and you should type the number of the room that I will write on the board now. So this is the key that SpeakUp requires. So you see here, I'm trying to build my private network. I'm using 10 dot something addresses. I have an Ethernet switch here, a router, another Ethernet switch, another router, another Ethernet switch. And the question I'm asking, here are the masks are all equal to this. Here are the addresses I've given to some of the interfaces. What is a valid possible address I can give to A? I close the poll in a few seconds. Closing. You should see the result. You should see that 55% of you have chosen answer A, which is the correct answer. That is the correct answer. So why is that? Well, the prefix is given by this here, which is the clumsy way of saying the first 3 bytes. Well, not so clumsy here. So that means the prefix is made of the first 3 bytes of any IPv4 address. Second, we should detect where are the subnets. So the subnets correspond to systems that are connected by the same local area network technology, which is, for example, Ethernet. Now, this and that are 2 different subnets because we go from A to B, for example, via different routers. So there is 1 subnet, 2 subnet, 3 subnets here. There are 3 different subnets. And IP principle number 3 says to every subnet should correspond a different prefix. So here we see that the prefix is 10.10.2, which is consistent. The 2 interfaces, of course, I'm showing only 2 interfaces, but presumably on Ethernet, I have many, many more interfaces that I'm not showing. Here it's 10.10.1, and here it can be only 10.10.3 because I've already committed the one address here. So this address should start with 10.10.3. So this is valid. This is not valid. This address can be allocated only to something that would be around here, connected to this Ethernet switch. If you do this, it will not work, because when the router B sends a packet to A router will, when B sends to this address, 10.10.2, it will not go to the router. The IP principle number 2 at B says, if I have something to send to 10.10.2.22, I send directly. So I will try to find the MAC address. I will send an ARP that will be broadcast to all systems. Nobody will reply because nobody has this address if you give it here. So B will fail. It will not be able to send to A. This is how IP works. As you can see, configuration, numbering plan is important. If your numbering plan is wrong, if you give this address to that machine, it doesn't work. Communication is broken. If we put things together, let's try to analyze and do what is called a packet sniffing exercise when B sends a packet to A here. So B is on Ethernet, A is on Wi-Fi, and it has to go via the Ethernet switch, via the router, and the Wi-Fi base station here. So here's how I can put all the layers together. B is perhaps a web server that is sending data to A as a response to a query. A clicked on a web page that resulted in messages reaching the web server, and now the web server is replying. So the web server, we use the socket interface. The socket interface will be something like this. You use a function call. We say send S2. S2 is the socket that you're using, and you send a data block here. This data block will be broken into 5 chunks that fit into IP packets. That's the principle of IP packet switching. That will be passed to the network layer. The network layer will add a header, adds to the data the IP destination address of A, that's in the green header here. And now we'll send it to the router via Ethernet. In order to send it to the router, it will add an Ethernet header that contains the MAC destination address, plus also its MAC source address. So via the cable, it will reach the Ethernet switch. The Ethernet switch will analyze the MAC header. It will see the MAC destination address. It will look in its table of MAC addresses. It will see, I need to send it to the interface of the router. So it will be sent to the router. So the MAC header here is the same, has not changed. But now the destination MAC address is that of the router. So the MAC hardware says, oh, that's for me. I should copy it. I receive this packet. And then I analyze the packet. I see that's an IP packet. It has a destination address, which is not me. If it would be me, I would pass it to an application layer in me. But here, I'm not showing this. It's not me, it's A. So I look at my IP routing table. My IP routing table says, oh, it's on link with me, but on a different link, on the Wi-Fi link. So I need to send it over Wi-Fi to the MAC address of A that I need to find by saying an ARP to A, if I don't know it. And now I create a MAC header, which is a Wi-Fi header, which is quasi the same, but a bit different than the one of Ethernet. Contains in particular the MAC destination and MAC source address. It's sent over Wi-Fi. It reaches via the base station, which I don't show here. It reaches the Wi-Fi adapter of A. It sees, oh, that's for me, removes the MAC header, analyzes the IP header. It says, oh, that's for me. It will pass it to the transport layer. The transport layer will look at the port number. The port number will say, oh, that is for this process, and I will make it available. The port number means it goes to a given socket. And then the application layer, sooner or later, hopefully, will read from the socket and will obtain the data here. So this is how all those things are put together. In terms of terminology, we have packets everywhere. The packets created by the transport layer are called segments, if it's TCP, packets at the network layer, and frame at the MAC layer, but not always. Sometimes people use the word packets also everywhere. In fact, things are a bit more complicated than what I just expressed, because what I've expressed is that a local area network is made of one Wi-Fi station or is made of one Ethernet switch. And in order to interconnect them, I interconnect them with routers, which is correct and true. Everything I'm saying is true in principle, except for mistakes and bugs. But sometimes I do approximations to make the thing easier to understand. In fact, you can interconnect local Wi-Fi areas and Ethernet systems with bridges, which are the same as Ethernet concentrators. So a bridge, an Ethernet concentrator is an example of a bridge. A bridge is an intermediate system that forwards packets based on MAC address. Intermediate system, that means it's a system that receives packets and sends them forward. It's not the destination nor the source of the packet. A router is an intermediate system. An Ethernet switch is an intermediate system. On one port, it receives a packet, it analyzes the MAC destination address, and it sends it forward. But you can do that on any kind of port. You don't need to do it just Ethernet to Ethernet. You can do it Ethernet to Wi-Fi, for example. So you can have a bridge to interconnect Wi-Fi to Wi-Fi. And worse, you can also put several bridges together, which solves a problem. You went to Migros because you had a few things at home. You have a server, disk server, media server, a printer, and a few things. And you bought a switch that has 4 ports. And now you need more. So what do? You throw away your bridge and you buy a bigger one, or you connect another one into this one, like you expect to be able to do if you buy extension cords that have multiple sockets. You can plug one in, and etc. For purely electrical things, you should not do too many of this because there are also safety problems. But for bridges, it's exactly the same. If I have one bridge that interconnects things, I can interconnect bridges together via Ethernet things, or by putting Wi-Fi interfaces if I have a bridge that has Wi-Fi interface here. And I can plug them all together and create a network here. And the principle of learning applies to this, so they will need no configuration. With a caveat, if you create a loop, like I'm showing here, I'm connecting everything to everything, so I'm creating a loop. This learning system has problem if there is a loop. Also, the broadcast has problem if I send a broadcast. Remember, at the local area network, we do broadcast. We do broadcast when we are learning. We have never seen this address before. Or we do broadcast when we do ARP, also for learning the MAC address. So the broadcast, if there are loops, then there could be problems here. Of course, the problems can be solved. The way the bridges solve the problem is to avoid loops. But they avoid it in a smart way. If you go to Migros and you buy 3 bridges, you connect them all together, you create a loop, then it will still work because the bridges are and MAC layer is supposed to be completely free of configuration. So if there would be something written on the bridge with a big exclamation mark, danger, don't create a loop, sure, somebody one day will still create a loop at Murphy's Law. Anything that's possible to happen with non-zero probability will happen one day. So the things that bridges will do, they will speak to each other by sending discovery packets. So B1 will send packets to B2, B1 to B3, B3 to B2, and they will discover that there is a loop, and they will speak together and come to a consensus to disable one of the ports. If you don't configure anything, it's random. One of the ports will be disabled. Now you can say, what's the point of creating a loop and then disabling it? Well, if that's for reliability, you want to create typically a topology that has multiple links for reliability. For example, if you disable this link here, and if, so that means all traffic from A to D has to go via B3. I assume for some reason this cable is cut, or B3 hangs. You put coffee on it and it doesn't work. So this bridge doesn't work. Then the bridges, who do that every few seconds, will discover that the topology has changed. They will discover there is no loop anymore. So this link will be re-abled, and then the learning will change, and A will be able to send via D. So it's completely automatic and plug and play, and it's called the spanning tree protocol that does it. It's a fantastic protocol, but we don't have time to discuss about it, and you probably don't need to know about it. The take-home message is simply, you can make a network of bridges with a limitation, of course. The limitation is every bridge has a table, which is an exhaustive table of all the addresses in your network. If you have a few hundred, the largest bridge network that I've seen are a few thousands, you have up to a few thousand systems that works. But you cannot do that at the scale of the internet. We can have millions of entries. So that is still local area, but can be bigger than a single bridge here. For example, you could put a bridge here instead of a router between your Wi-Fi and Ethernet. In fact, that's the most usual configuration. If you have at home a small network with Wi-Fi and a bit of Ethernet, that's probably the standard configuration. That is simpler because by doing this, if you observe here, something has changed now. If you look at the IP addresses here, this is one subnet. The entire thing is one subnet. In fact, bridges are transparent from the viewpoint of IP. So when B sends a packet to A, there's no difference for B whether A is on the same Ethernet switch or not, if it's connected via bridge. There's no difference. B sends a packet to the MAC address of A, because the bridge here, there are two bridges here, the Ethernet concentrator and this one. They have tables that the first Ethernet concentrator knows it should be forwarded on this port, and this one knows it should be forwarded on the Wi-Fi port here. So they are on the same local area network, even though there are two technologies here. And A or B cannot distinguish whether the other systems are on the same system or not. Cannot distinguish by, I say, with Wireshark. Wireshark is a software that we will use in the lab to look at what's inside the packets. I've shown before a few anatomy of addresses here. So we can look physically, that's very easy to do. And if you look at packets, you will see if you look at B is sending to A. When B sends to A, there is nothing that indicates that A is on Wi-Fi. And similarly, when A sends to B, A thinks that B is on Wi-Fi here. And that's simpler. Why is it simpler? Well, because I don't need to do a numbering plan in my system here. I just need to have one prefix for me, which is probably given by Swisscom to me. And I don't need to build a larger, more complicated network for my entire system here. For example, as I said, when A sends to P, A will look at its routing table, will see the destination address is on link. Therefore, I need to send to the MAC address of P. A will send a NARC packet if A doesn't know the MAC address, that will be broadcast by the Wi-Fi base station, that will be received by the bridge. When the bridge receives a broadcast, the rules of the game of a bridge is that we forward it on all the ports, except the one it came, which is possible because we have a spanning tree. So that will not create a loop. There's only two bridges, so there's no problem. So the broadcast will be sent here on this port. It will reach this other Ethernet concentrator, which is a bridge. So it will forward it on all the ports. It will be received by P, and P will reply. So the ARP reply will come here. And A will send a packet to the MAC address of the printer. The bridge will send it, looking at its MAC address table. It will reach here, which will look at its MAC address table, and it will reach the printer. The same. The bridge switch is the same. Historically, there are subtle differences, like a bridge is, rigorously speaking, is an intermediate system of the MAC layer. It's an intermediate system, something that handles packets by looking only at the MAC addresses. So I say we analyze the packets at point one. How can we do that? Well, if we can log into the Ethernet switch, we can start a program called Wireshark in the Ethernet switch, or we can break a cable and put a repeater that is also a splitter that will split the electronic signal so that we can pretend we will observe everything. That's what hackers will do. So whatever the mechanism, I assume I am here and I can observe all the packets that flow here. And B sends the packet to A, and we look at the destination MAC address. What should we see?
From what side are we looking, from A side or B side?
So B is sending to A. That's what the arrow means.
One, are we observing it?
So we are at one, and we see the packet as it flies here. I wait a few more seconds for the answers to improve. Voila, now it has improved, so I can close the poll. I wait until the majority is correct. Right. And the experts in that kind of tools, they say that if I give the hints that you're wrong, but I don't say who is wrong and not right, normally it gets better because the truth imposes itself with more evidence than, I'm not sure it's true, at least for other domains, but here it worked. So I'm closing the poll. And the short majority says A, which is correct. Here we have a router. So we have two subnetworks, and B is sending, therefore, to its default gateway. So it's sending to the MAC address of the default gateway, which is A. Yes? Here, this box is a router, which means a router separates two subnets. Okay. Now, IP principle number 3 says I have a packet to send to A. I need to go to my routing table. And the routing table will say, go to the router. It will not say go directly to A. I would say go directly to A if I am on the subnetwork. If I send to P, I would say that. But A is not. So I need to send to whom? To the router. So to the MAC address, which is this one. Yes? I don't know. That's the next question. That's the next quiz. What's the IP address? Of course, I've looked at the MAC address. I close the poll in a few seconds. Closing. And now the vast majority says C, which is the correct answer. So the principle of IP is we send a packet to the IP destination address in all cases. So the IP destination address is this one here. Let's continue. What's the difference with the previous case? That the box in the middle is a bridge. As a consequence, you see that the addresses have changed also. The same question. B sends to A. We observe the packet at point 1. What's the MAC destination address?
Which same as layer 2 device?
Is the bridge?
Same as layer 2 device.
I'm not sure what layer 2 device means, but the bridge is a layer 2 device here. Yeah. Yeah. I close the poll in a few seconds. Closing. And the majority says C, which is the correct answer. Now last. Closing in a few seconds. And the majority says C, which is true. So the IP address is this one, which is the final destination address. So you see that from the application viewpoint at B, you send to this address, whether you're on the same subnet or not, is completely irrelevant from the application layer, which is a desirable property. We would not like to have software that at the application layer needs to do things differently depending on whether the destination is on the same subnet or not. That would be ugly. So another questions I could have asked is, another option I could have inserted is, there is no IP destination address, which would have been wrong, at least if we use TCP-IP software. So even if everybody is in the same subnetwork, we do use IP addresses as long as we use TCP-IP software. As I said, there is exotic software that can live without IP address, but it's really exotic. It tends to be old and no longer used or no longer developed very much. Well, let's continue. So we've done the major part in terms of difficulty, which is putting together IP and MAC. And if you've correctly answered those 4 quizzes, you have at least a good part of the notions in good place here. So this is, I would say, the major complexity and what is mostly poorly understood. If you look on the web and everything, people usually say anything randomly about those things here. So in a summary, the MAC layer is used to interconnect things, could work without IP address, was originally designed to work without IP addresses, but we still always use IP addresses everywhere. And we interconnect subnets via routers. We can think of subnet as a given MAC technology, but they can be interconnected by bridges. Now, the questions, of course, is when do I put a bridge? When do I put a router? So in this example before, why should I put a bridge or a router? The answer is you can do both. There are obvious answers. If you have 200 systems here and 200 systems there, you will probably put a router because of the broadcast, everything. So rules of the thumb, a rule of thumb is typically a subnet. You don't want to have much more than 100 devices in a subnet today, because there are broadcasts inside a subnet, and the performance might not be optimal. Question?
Can we build all of around the world just with the bridges?
Yes, you can make bridges. As I said, I've seen networks at CERN, for example, that had up to 20, 30,000 devices. It's possible. But it tends to be obsolete. The price to pay is to have bridges that are very high performance. And you avoid, what do you avoid if you put a bridge? You avoid the complexity of the numbering plan. You can put one big subnet for everyone. And in particular, if you move devices, if B moves from here to there, it will keep the same IP address, which is convenient. So it's more convenient. In small networks, you will tend to bridge things. So home networks are typically bridged. There are also limitations. There are systems and applications that work only inside a subnet. Perhaps if you use connected audio systems, that's you send your audio from your smartphone to a connected speaker or amplifier, or you use Apple's AirPlay, that works only in the same subnet, because you don't want to have your audio that's starting to leak over the internet and go everywhere, because you consume a lot of resources by doing that. So if here you want to do AirPlay from A to B, that will work. If you put a router in between, it will not work. So some systems have been designed with the hypothesis that the source and destination are in the same subnet. This is also sometimes used for security purposes. For example, if you have a very touchy application, for example, your accounting application, you expect that it's reachable only by systems that are in the same subnet as you. To avoid, so if you want to work on the software, on the accounting software, you have to physically come to places that are connected to the same subnet. This reduces the perimeter of attacks. So, you can still be attacked, but you have to be physically present in the room. So there are applications that do this using a field that's present in the IP packet called time to live. Whenever a packet goes via a router, its time to live is decremented. If you put the time to live equal to 1, that means it cannot go via a router. So it's possible to force some application software to work only within a subnet, and a few applications do that. Now let's move on to another related topic of names. When we connect to systems, very often we use names instead of addresses here. So names were originally defined as human-readable synonyms for IP addresses and other things, not just IP addresses, but in our context, this is what it's used for. For example, if I use ssc.epfl.ch, if I go to this machine, it's instead of giving the IP, if I go to a web server, I typically don't give the IP address of the web server, but a name. Yeah. So names are organized in a hierarchical form where more specific is at the beginning, more general at the end. And the last block, which you know, of course, is generic. For example, .com means anything commercial. Any name that has applied to a domain.com, and the intention is to have companies. Two-letter names are allocated to countries. So Switzerland has the CH, New Zealand has NZ. I'm not sure what this country is, but there is a country that has a GL, LI has Liechtenstein, etc. They can be reused for other purposes, but this is allocated to countries. So if you want a domain name that ends in CH, you have to ask a registrar who has received a block of names and or who will apply for the name, and the ultimate authority is in Switzerland. For example, it's Switch in Switzerland that controls the ultimate allocation of names. For example, if you would like to say, oh, I want to take the name epfl.ch, and well, it's already taken, and if you want to dispute this, but I am EPFL, it's not okay that someone else has the name, the dispute will be in Switzerland, and that because this has been allocated to Switzerland. So this is the implication of those names here. That was the origin. Originally, the names in the internet were either 3 letters for generic, not country dependent, or country dependent in 2 letters. Then it's been open to any names. If you pay $500,000 a year, you can have your own name, whatever you want. So IBM, UBS, etc. When this was open, so a company bought this name, Sachs, and created things like this to blackmail companies like Apple. So that's a true historical fact. So you can buy names. So they found a way to make name out of money, to make money out of names. For us, the interesting question is, where are the names in the packets, for example? So the first answer is they are not in the packets. When I go to a website like this one, ssc.epfl.ch, so I'm surfing the web, I find a page, and this page gives me this. I found a page or an email or something, although it's a bad idea to click on a link in an email, but I have received some information that the thing I should go to is ssc.epfl.ch. What will happen? Well, I will need to send packets to this to open a connection, probably a security association with this, as we will discuss. But I will not be able to go to this server. Sorry, the server is here. Before going there, I will need to find the IP address that corresponds to this name. And this is stored in servers that are called a DNS server. DNS is domain name system. And there are servers. Whoever owns a block of names must have a server or rent a fraction of a server in which there is a file giving all the IP addresses that correspond to all the names here. For example, here, this name is epfl.ch. So EPFL has bought from Switch the epfl.ch name. So Switch has put in its server an address that says the DNS server IP address of epfl.ch is whatever EPFL gave. This one, for example, 128.178.15.8. That's the DNS server of EPFL. That's written in the big record of Switch. And then EPFL owns all the things that end in epfl.ch. If you want such a name, you have to ask permission from the EPFL network managers, who will give it to you if you have a good reason to have such a name. And then they will write in their server the IP address of the web server that corresponds to this name. For example, ssc.epfl.ch will correspond to a given IP address, which is 51.13 here. That will be written in this server. And all servers in the world will have a way to eventually go to this server by going step by step. When we do this here, we will go to this server. We go directly to the server if we're at EPFL. That's an easy case. If I'm on the Swisscom network, I will first go to the Swisscom server. The Swisscom server will not know the answer, but the Swisscom server will know what is the IP address of the switch server. So we'll ask the switch server who has more information about epfl.ch, and then the switch server will give to Swisscom the IP address of the DNS server of EPFL, and then we send our query to this DNS server of EPFL, or the Swisscom server will send. So using an application called DNS, our system will in fact go to the DNS server and send an application layer packet. IP destination address is that of the server, and there is a text, a message that says who is ssc.epfl.ch. The server will reply if the server wants to. Typically, EPFL DNS server replies only to people that are at EPFL or people who are DNS servers themselves, because we don't want to serve the entire world to avoid denial of service attacks, for example. So if it decides to reply, it will reply to me saying, how does it know it's whom to reply to? Well, my IP packet contains my IP source address. So by looking at my IP source address, I can reply to me, and the reply will contain a message saying, this is the IP address of the server. All of this is happening while I click. So when it says you click and you see it's waiting, well, it's waiting because it's finding the IP address of the server. Now that I have the IP address of the server, I can send an IP message that contains an application layer message that goes to the server, and the reply will come back in one or several messages with the images, for example, here. So you can try NSLOOKUP on any machine here, and you will be able to simulate this. If you try NSLOOKUP with a given name, you will have the IP address or the multiple IP addresses that correspond to this name here. So thing to remember, IP addresses, not names, are present in IP packet headers. So the internet routers, they look only at names that are contained in IP addresses that are contained in IP headers. They never look at names. The names are probably somewhere in some of the packets. For example, if I go to a web server where I will say, I am connecting to you, and perhaps the name I'm going to is contained in the first packet, but the replies will not contain it. For example, the replies will contain the images I'm sending. One command we'll use in the lab is the ping command, which uses name. The ping command is a very useful command that is used to connect to other servers. So it sends a test message to a name or to an address, and it gives you replies. For example, on a Macintosh, I believe, yeah, this was a Macintosh, but it's the same on Windows or even on smartphones if you use the application I gave in the lecture note. I'm trying to test this address, which is in New Zealand, canterbury.ac.nz, and I'm saying send only 3 messages. So it sends 3 test messages. There are variants of pings. There is ping ICMP and ping TCP. Those are details I will skip here. And it gives the TTL, the response time, 300 milliseconds. So it says that's the time it took between me sending the reply, the server in New Zealand receiving the reply, or the machine in New Zealand receiving this reply, the reply coming back to me. 300 milliseconds is a reasonable time to go to New Zealand and back here. If I do the same thing to Zurich, I will have a reply time of a few milliseconds here. 0 packet loss means no packet was lost here. I also see the TTL. Remember, I mentioned this TTL field. When a packet is sent, it has a field that is decremented by 1 in every router. And what we see is the value when it comes, when it reaches us. Here it's 48, which means probably, I'm guessing, but I'm pretty confident that ETH puts a field of 64. That's the default value. When you send a packet, you put 64. and then you hope that there is not more than 64 routers in the path, otherwise your packet will be deleted. And here 64 minus 56, that's probably 12 hops in the path between Zurich and us here, or me at home here. New Zealand, the TTL is 223. That means New Zealand, which is very remote location, they believe 64 might be too risky. There might be many, many more hops away from anybody else. They probably put a value which is larger, probably 256, 255. And when it reaches us, it's 223. So they've consumed about 30 plus hops here. Incidentally, the ping command will go to DNS, because here I said ping to this name, and when I see the reply, I have the IP address here. The IP address is not in the ping packet. Sending a test packet. What ping is doing is exactly what I showed in the previous slide. The ping software, which is an application layer software, goes first to the DNS to find what is the IP address of the destination and sends a ping packet to this. And when it prints the result, it will print nicely for me to the name and the address. So ping is another way to discover the mapping names and address, because if you ping to a name, you will have the address. Traceroutes is another useful program that does a bit more. Traceroutes detects all the routers between me and the destination. The way it works, it sends first a packet with TTL equal 1. The packet with TTL equal 1 will try to go to the destination, but will be deleted by the first router, because the TTL1 allows it to cross 0 router. So it will go to a router. The router will say, oh, I should forward this packet. That's my routing table says. But the TTL is 1. This packet is too old. I should discard it. And most routers, not all, but most or many routers, when they have this, they send an error message back to the source saying, I should have forwarded this packet, but I could not because the TTL is exhausted. And then the source, the traceroute software, will see this error message and will see, oh, I have an error message coming from this router. That's the first hop on the path. This is what it's doing. So it has sent a packet to New Zealand, and the first router on the path, so this is from EPFL, is called CVDISBV exactly. That's the name that the EPFL system managers are given to the first router. And you see its address here. So I was on the I was in my office on the network 151, and this is the first error message has come from you. And then the traceroute software sends another packet with TTL equal 2. The packet forward goes towards the destination. At the second router on the path, same thing, an error message is sent, and etc. until the end here. It does not always work. Some routers don't send error messages. Routers of academic networks tend to do it. Routers of commercial networks sometimes don't want to do it because they are, well, it consumes CPU. It consumes resources to send error messages. And it's a way to attack also a router. If you want to bring a network down, you create robots. You first infect millions of systems that will start pinging, flooding with pings, with trace routes, a given destination that will force all the routers on the path to do a number of those things, which might bring the routers down. Modern routers have a way, they have a rate limitation. They send a number of error messages per minute, not more. So if there is an attack and if doing traceroute at this time, this router will not reply and you will not see the paths on the way here. You can do more. You can use Wireshark and look at a packet. For example, you will see in the lab the details. Here, I did my trace route and I looked at one of the packets sent by my machine. And here's what I see. I see it's an Ethernet packet. It is sent to this destination, which is my default router from me. And now you see name AVM audio. The names are simply extrapolated from the MAC addresses. MAC addresses should be unique in principle worldwide. How do I make sure that the MAC address of this, when it's using Wi-Fi, is different than the MAC address of this when it's also using Wi-Fi? Well, because the MAC addresses are given by blocks to providers, manufacturers. Somebody made the Wi-Fi adapter of this, and the company that made the Wi-Fi adapter received a block of MAC addresses and then gave addresses here. And the blocks are well known. They are public. So the Wireshark software knows that C80E14 is a block that has been allocated to this manufacturer. This is how it knows about it. Then it's an IP packet, this trace route packet, that is sent. You see the time to leave 12. So it means this packet is trying to guess the 12th hop. And to whom is it sent? To this destination address here. So this is not to New Zealand. This is to ETH, and this is sent, this is not from EPFL now, it's from me at home here. That's my home address. You see, it's a private address. We'll talk about it a bit more. And then it's a UDP packet, that's the transport layer. It is sent to this port from this port. And then it contains essentially nothing, just contains 0, because this is simply a test packet here. Voila, this is for the names and addresses. I will conclude today's lecture, which is a bit heavy, but this is how it is, with the last ugly thing of the story, which is IPv6. So we could stop there and everything would be simple. But unfortunately, your generation will be confronted with the fact that there is IPv4 and there is IPv6. So the most widespread version of IP is IPv4, but the most recent one is IPv6. Why a new version? Because 32-bit is not enough. 32 bits means 2 to the power 32 possible address, which is 4 billions, 4 10 to the power 9. There are probably close to 10 billion people on Earth. Sooner or later, everybody will have a smartphone and a few computers, and we need several addresses per person, so that's not enough. At least if we don't use NATs, as we will discuss next week. So if you ask, for example, a block of IP addresses in Switzerland, you will not have it. A new block. The only way to obtain IP addresses that have been allocated to Switzerland is to find someone who has them already and resells them to you. So used addresses, if you want. New IPv4 addresses cannot be obtained anymore. But you can obtain IPv6 addresses. This is why IPv6 has been used, has been developed. So it extends the address field to 128 bits. So instead of 32, it multiplies the length by 4, which means that the number of possible addresses is to the power 4. Now it's a true astronomical number. The number of possible addresses is 10 to the power 38, which is truly astronomical. It's a huge number. It's much less than the number of atoms in the universe, but still is an astronomical number. So we could put an IP address probably to every molecule on the surface of Earth with such an address space here. The good news is that it's just an addressing plan change. The rest is as before. The IP principles 1, 2, 3 that I've discussed before are exactly the same. That's the good news. The things are exactly the same. But there is still a bad news, is that for some reason that appeared to be good at that time, and in my opinion appears to be bad today, the IPv4 is incompatible with IPv6, which is a bit weird. It's like if I buy a telephone here, you might remember, you were probably already born when there was a major change of numbering plan for telephone numbers. When I arrived in Lausanne, if I would call somebody in Lausanne, I would not dial 021. I would just dial the number without the 021. Then the 021 was added. Then Zurich was 01, but it became 41 or 44. And so there was a change of numbering plan, and other countries have done more dramatic plans. In France, they've added digits but the telephones have not changed, right? Here, well, we don't change the smartphone, but the software needs to be changed. If I have an application that has IPv6 and IPv4, they have two incompatible things in the sense that if I send an IPv6 packet to a machine that has only IPv4, the receiving thing will not be able to decode it, which makes sense. If I extend the numbering plan, I had an old number that was 6-digit, and or let's say 32-bit, I give you a number that's too large, I cannot parse it. But it's also the other way around. If I send an IPv4 packets to an IPv6 machine, it will not be understood. They are treated as different things here, which in my opinion is an error. An IPv6 machine could understand an old style packet by saying it's only 32 bits. It means that's the old fraction of the numbering plan. But the decisions were to make them distinct. Probably they were influenced by Apple. You know, when Apple creates a new operating system, all the old ones are no longer compatible, as opposed to Windows, where you can continue to have software. You can have programs that were done for Windows 95 that will continue to work in the so-called compatibility mode on Windows 11, for example. But there's a price to pay. Windows software is typically less nice and more clumsy, more error-prone as the reputation it has. So probably that's the reason. In order to make things simpler, it's incompatible. Now, that's no big deal from if you have both, which is true for all the systems in this room, are probably IPv6 and IPv4 compatible, because your latest version of Apple software or Windows software, by necessity, will run both IPv4 and IPv6 here. But it's not true of any network. You have networks that give you only IPv4 access. In fact, the EPFL Wi-Fi network has been offering IPv6 only since this year. Last year, there was no IPv6 on EPFL's Wi-Fi network, and they did it because I've been asking this for 15 years. So after 15 years of asking and the change of vice president, they eventually accepted to do it. Why do they waited so long? Not because they're stupid or bad, they're very smart, but they are just money concerned. It's a change of software on all the routers and all the base stations of EPFL. There are 1,000 base stations at EPFL Wi-Fi here. So it's like a major change. It took them 1 year to do the deployment of the new change. And as usual, when you change software, even if you do exactly the same thing as before with new software, there are still bugs and things that don't work. So it's a major change from one to the other. So in the smart grid, for example, most smart grids that I know work only with IPv4 for this reason. Why should we change? It works the way it is. Why should you change? Well, if you're a network that's emerging, for example, if in India you deploy a new cellular telephony network, you will receive only IPv6. You need 100 million new addresses, and you will receive only IPv6 addresses. So there are parts of the world where they have, because of the growth, they need to have new addresses, and they will have only IPv6 addresses. So you have IPv6 only networks. Now, in order to, those two don't work together at the network layer. You cannot, so you will need to find clumsy situations for them. Another part of the ugliness is that what happens when you move from 32 bits to 128? Well, this is an address now. That's my EPFL address on my office, on my computer in my office here. The local host is this address here. It's one. So things have been simplified because IPv6 now, things I've learned from all the ugly things of IPv4. They've tried to make it more systematic here. But still, the address is very long. So the first thing we must learn about IPv6 addresses is how to understand them correctly. And there is a so-called compression rule. So first, we write them in hexadecimal, right? Here, I did not write in binary because writing 128 bits is truly ugly. Yeah. So it's written in hexadecimal. So when I say 2, it's not the decimal number 2, it's the hexadecimal digit 2. So you can see also F, D, E, which are, you see hexadecimal digits here. And we group them by block of 4 hexadecimal digits, which correspond to 16 bits. 4 times 4, so 16 bits. They're separated by columns. And the compression rules is that you can omit leading zeros. For example, if I have here 0A00, I can write it. I could write it, so I don't have here, but my address here, the 0620 can be put 620. I said 20, but this is wrong. I say it, everybody says it, so I repeat what everybody says so that you're exposed to the true reality of the world in which we live. But it's not 20. Why do I say it's not 20? Because that's hexadecimal, right? It's 2 followed by 0. So 2 the second digit means I multiply by 16. So it's 2 times 16, 32. Right? So this is 20 is 32. But of course, I don't have a computer implanted in my brain yet. So when I see 20, I think 20 and not 32. So those are the numbers. And you see they have been allocated. The numbering plan that's currently allocated is this one. You see it has been allocated in year 2001. That's why but again, it's not 2001, it's 2001. And we can also, any groups of zeros can be replaced by an empty string, 2 columns, which is a convenient way of saying the loopback address. So if I send an IPv6 packet to myself, I send it to this address here. And here I see also I have an address here that has plenty of zeros in the middle. I can compress it here. Of course, there can be many times zeros in addresses. I can compress it only once here. So if you do if config on Linux or Macintoshes, IP config on Windows, you can see your address here. I see that on this machine, I have an Ethernet interface. Here I see my MAC address, which is written in hexadecimal. I have an IPv4 address with the net mask here. Interestingly here, I believe this is a Macintosh. It writes, you see that it writes the mask in hexadecimal digits. The mask is typically written in dotted decimal, but probably influenced by, I'm not sure why, it writes it in hexadecimal digits. And here I have an IPv6 address here. And similar to IPv4, there is a network mask. But for IPv6, here you say it's called prefix length 64. That means my mask is the first 64 bits. 64 means just half. That means the first 4 blocks here are just the blocks of that corresponds to my network mask here. Worse than that, in IPv6, every interface has, in addition to its normal address, like in IPv4, a thing that's very special that has been invented for IPv6, and is called the link local address. It's an address that can be used only inside the same sub-area network, the same local area network, inside the same subnet. So to understand this, we need to understand the MAC layer, which we did before. And those addresses start with FE80 here. So every interface will have such an address. And I will conclude with this here. So if I look, for example, at those different machines, a machine like this one has an IPv4 address, has an IPv6 address, and has an IPv6 link local address. The rules of IPv6 say if A sends a packet to B, and for some reason I want to make sure I will stay in the same local area network, then a good way to do that is to use the link local address as source and destination. You remember that Apple AirPlay or some finance software, they want to restrict access to a subnet, to a local area network. In IPv4, you have to manipulate the TTL for that. In IPv6, you can use addresses for that. That's one use of that. I believe the major use of that is that IPv6 intention is to get rid of the MAC layer. Imagine in a distant future that we don't use MAC layers anymore, but we use only the IPv6 link layer addresses here. That would be possible, but it's a dream of the future. And in the present, where we live today, it just makes things more complicated, but it's a bit less complicated if we understand what a local area network is. Other than that, IPv6 is the same as IPv4, but it makes it a bit tough. And since we are 2 minutes late already, I thank you for your patience. Invite you to do the quiz. You can do the quiz already now as a preparation for the lab, and then the lab.